Hello, and welcome to this course on IoT security. In this first module, we're going to define IoT, or the Internet of Things, as it is not a formal industry term, and it can mean different things depending on who you ask. This course will cover fundamentals of both IoT and security, but ideally, you should have a basic concept of both. IoT. It stands for Internet of Things, where things are physical objects with IP addresses, and we should assume that they are connected to a network. They have some sort of input capability, such as a sensor, can receive and process data, and can also communicate with other IoT devices, generally without an intermediary. For example, a clothes dryer that might be able to sense that your clothes are dry and shut itself off to conserve power, then send a notification to your mobile phone to notify that the cycle is complete. Consider the Internet of Things to be billions of connected devices with some level of individual intelligence that's comprised of smart devices, smart energy meters, smart homes, smart cities, smart grids, and so on, all communicating with each other, non-human objects, or entire systems. This level of connectivity yields a tremendous amount of data which is constantly being processed and distilled into useful information that can serve as input to control things around us, to make our lives and jobs easier, safer, and even friendlier to the environment. As this is a course on securing IoT and IoT devices, I want to draw attention to the most relevant parts of our definition of IoT. They are physical objects with network connectivity, input capability, the ability to process data, and the ability to communicate. These properties are extremely important when thinking about how to secure IoT devices. So, we have just covered how we define IoT for the purposes of this course, and next, we will look at the basics of security so that we can layer the two concepts later in the course. In the previous segment, we defined what IoT is. In this segment, we'll take a look at some security primitives and why they're important when thinking about IoT security. Security can be similarly ambiguous as IoT, so let's set out some security fundamentals for the purposes of this course. At the heart of any security consideration, especially in context of IoT, is the protection of data. The topics we will discuss here are identity and access management, data protection, network security, logging and monitoring, and physical security. Identity and access management. With more and more devices with network connectivity that are transmitting data between themselves and other targets, being able to granularly identify each device becomes an essential part of securing access to them. Logically, because it brings context to the data being transmitted. This context is a precursor to guarding access to systems which the devices are meant to inform. The first half of identity and access management is identity. Being able to specifically identify an individual device from the next one has logical benefits as well as security ones. For example, if you were managing a fleet of smart energy meters for a municipality and one of them stopped communicating with the central communication system, how else would you know where to send the repair truck? Similarly, in context of security, if someone were to do something nefarious to that smart meter and it has become a threat to your systems, it would be paramount to know which device is the cause of this disruption. Identity, therefore, is a prerequisite to access management. Using the same smart meter example, if you have a system that can be managed by an administrator, including the administration of billing and the distribution of energy, without the differentiation of identity, how could you reliably prevent the device inside the home from performing an administrative task? Data protection. Generally, the level at which data is protected is commensurate with the sensitivity of that data. For example, personally identifiable information, or PII, is generally regarded as the highest classification of data, and should therefore be protected accordingly using strong encryption and oftentimes other mitigating tactics. Conversely, Public information may not require any consideration at all, as the compromise of that data has no impact. In context of IoT, a camera that is doing facial recognition would contain PII, whereas a device that reads and reports the temperature of its immediate environment does not require any special handling, as anyone can measure the temperature for themselves if they choose. Network security. Network security is of utmost importance in an IoT context, as the devices are not only network connected, but they often have the ability to communicate with each other without necessarily communicating through a central source. To complicate things further, depending on the nature and physical location of a device, this could be done over one or more networks, not all of them known or trusted. Securing the network is fundamentally about ensuring the data being transmitted from one device to another maintains its integrity and is done so deliberately. Logging and monitoring. Logging and monitoring is a cornerstone of the long tail of security. Logging will tell you the path that a given device has taken, which can be insightful when making decisions to make modifications to the security properties of a device, isolate it, or even destroy it. Monitoring gives you the ability to measure what normal activity looks like so that you can detect and alert with certainty when a device is behaving abnormally. Physical security. As we have defined IoT as physical objects, we need to consider their physical security. Considering the low cost of most IoT devices, you could assume that the device itself is more or less expendable. That is not to say that we don't care for the safety of the device, but it does mean that there is a cost versus benefit judgment on how secure you make a device physically, as well as consideration for other mitigating security elements or techniques. For example, on the extreme end of physical security, you could use tamper-proof screws to hold devices together, or maybe even have the circuitry dipped in a non-conductive epoxy that once dried could never be accessed. But the cost of the device is only a fraction of what those mitigations will cost, and you have to secure hundreds or even thousands of devices, then you may want to look for other ways to ensure that the physical device is safe, or more sensibly, that a physical compromise of a device will not impact your overall security, or at least very little. This, in the security world, is what is known as the blast radius. It is most likely more sensible to think of mitigations to other aspects of your IoT device's physical environment before considering direct modifications to the hardware for the sake of security. For example, if you install smart light bulbs in your home, you should not need to ensure any device-level physical security measures, as it is assumed that the devices are within the physical boundaries of your private home, which we should also assume is locked and generally only accessible by individuals who have a key. In that example, it is also worth noting that the data being transmitted by these light bulbs is assumed to be low risk, and that even if they were exposed to the physical world, they have a very small blast radius should one of them be physically compromised. But more on that later in the course. So, instead of improving the physical security of individual devices, start thinking about ways to reduce the blast radius of a device that has been compromised. Now that you have a good idea of what your security priorities are, the next segment will cover what security challenges typical in IoT systems are relevant to the fundamentals I just discussed. In the previous segment, I briefly covered the security primitives that are fundamental to IoT. In this one, I will surface the main security challenges that IoT faces. These security concepts I've just covered are not unique to IoT devices. In fact, they predate IoT entirely and have been around since the beginning of modern IT infrastructure. If we conceptually replace an IoT device with a server, the same principles apply. Identity and access management, data protection, network security, logging and monitoring, and physical security. So, if these things are already known, why do we even talk about security in an IoT context? Why can't we just apply what we have known about these topics to IoT devices and call it a day? The challenge that IoT brings to security is not necessarily a challenge of practical application, but rather a challenge of scale. Take data protection, for example, or more specifically, encryption. Encryption has been the primary security countermeasure for protecting data at rest for decades. The computation and operation of encryption is so standard these days that it is all but an afterthought. Encryption is easy. It's the key management that becomes challenging at scale. If you're encrypting a hard disk on your server, you will likely have a single encryption key. That key is used to encrypt and decrypt the storage blocks once written to the disk. 2 disks, 2 keys. 10 disks, 10 keys. Now let's consider the magnitude of IoT. It is estimated that by 2020, now let's consider the magnitude of IoT. It is estimated that by 2030, there will be up to 125 billion devices that are connected to the internet. If only even 10% of those devices are carrying data worth encrypting, then there needs to be 12.5 billion unique keys. Not only do you need the keys, but you need to keep track of which keys encrypt and decrypt which devices. Couldn't you just use the same key on multiple devices? Sure, but that increases the blast radius of a single device. If someone were to gain access to your physical device, they could intercept the key and use it to get data from other devices. Imagine if every door on your street used the same key. So, in an IoT world, how will you ensure that the data you're getting from a device is reliable? How do you know that the communication is authentic? Network security is another priority for IoT devices, because we don't always know how many hops a device will take before it can transmit its purpose. If we consider your smart home lighting setup, the lights are probably communicating with a base which is communicating directly with your home Wi-Fi, all of which in a relatively trusted, or at least predictable, channel. In that case, the network security of those devices is going to be the exclusivity of their communications to ensure that they aren't also communicating with another base station, so that someone could not set up a rogue one nearby and start controlling your lights. The scenario might seem innocuous, but now replace smart lights with a smart door lock, and the risk becomes apparent. In more industrial IoT applications, for example, sensors that transmit telemetry of a wind turbine in a wind farm, communications might travel a vast distance before they reach their intended destination and traverse several networks, none of which you own or have control over. This scenario gives life to a buzzword that is out in the security world known as zero trust environments, where even when we know the happy path a device might use to communicate, we should be skeptical of every single transmission, as the integrity of one message does not correlate to the integrity of another. This is another promotion of the importance of identity at scale. As you can see, IoT presents more of a challenge of scale rather than preparing for the unknown. In this course, we set out to address these challenges in a practical and realistic way. We will aim to apply modern spins on the known security techniques that have been battle-tested for decades.